All right, good morning. Hope you're all enjoying your almost complete first week of cider. We're going to do some thermal structure, modeling and evaluation thereof of subduction zones. We're going to be looking at how deformation works. You're going to be deforming stuff this afternoon. Squeeze those rocks. Or paraffin, as the case may be. Oh! I gave the trick away. What did you guys get for seismic tomography? Did he put B. Brandon Schmant in there as the solution? That's what I would have done, but... and then this afternoon we have 2 research talks. And that's the schedule for today. So I originally was signed up, I think, to do the thermal structure and dynamics of subduction zones, which is a really large topic. And since we have Thorsten and Magali present really good perspectives on the dynamics, I'm just going to focus on the thermal structure and not on any of the pesky dynamics that comes in there. Well, there's a little bit of dynamics, but this work, Cian helped us with it. Also introduce a little bit the tutorial, which will look at how do you model for a very simple model, the structure of subduction zones, that we'll be doing next Friday afternoon. So the game, or the plan of attack, is to provide a little bit of perspective, how people have modeled subduction zones, starting right when plate tectonics became accepted as the new paradigm in the late 60s. Going to look at one specific approach to model the thermal structure. For well-known subduction zones, we can assume where the slab is and how fast it's going, and then let the model evolve to see what the temperatures are at depth across the slab and in the mantle wedge. In order to do that, we'll look at the equations, we'll look at how do we solve these equations, and what internal measures do we have to know that the answers we're getting out of that are accurate solutions to the differential equations we impose on it. Then talk a little bit about what the sources for uncertainty and error are, which lies particularly in the applicability of these models to real settings rather than the actual solution of the differential equations. And then, just to throw all caution to the wind, I'm essentially going to throw everything in the kitchen sink at these models, meaning all observations we have, and then see if these models are left standing at the end of that comparison. So the goal for these thermal models is to predict what the conditions are at depth that may help explain all of these processes that are going on in the mantle wedge, and I probably excluded a few. Cold incoming lithosphere, sediment maybe being scraped off, increased pressure, increased temperature causing dehydration reactions, which may or may not be related to intermediate depth seismicity. The fluids penetrate the mantle wedge, cause flux melting, that eventually, for a variety of stages, ends up in the arc. We think we have this cold corner. The sediments may form little diapirs. There could even be a little bit of decompression melting due to the upflow of material in the mantle wedge. And then, once this slab is being nicely processed in the subduction factory, it goes down, and then you could ask questions like, well, how much water, how much CO2, how many goodies go down that can then explain the long-term geochemical and thermal evolution of the Earth. This is a very complex cartoon, well, complex set of assumptions in there. An important, and we haven't maybe talked enough about this, a very important part of the physics of the mantle wedge is the corner flow, which is indicated by this curvy arrow. The corner flow is set up by the fact that this slab entrains the overlying mantle wedge. It gets viscously coupled, it drags this wedge down, and as a consequence you create a hole. And nature doesn't like holes, and therefore it needs to be filled in. Essentially you get negative pressure here. This needs to be filled in somehow, and in this perfect two-dimensional setting, the way that this flow comes in is from far away, and that's being brought down again. This corner flow therefore sets up a very efficient conveyor belt system where you continuously bring in cold and hydrated stuff that sees hot mantle wedge, and therefore you get a huge amount of productivity and reactivity. That is that subduction factory, and the corner flow drives the subduction factory. If you have a three-dimensional setting, for example, you sit at the edge of a slab, of course this negative pressure could more easily be filled in by flow from the side. And so keep in mind that this is a highly simplified and pure 2D thermal or cartoon. So to amuse ourselves a little bit about what people did way back when, I think Brandon mentioned he was in 3rd grade when this fantastic experiment in Oregon happened. I was, I'm not going to tell you how old I was. I was alive, but I did not hear about the great Mackenzie when this paper came out, I will tell you. Dan Mackenzie, I think, provided the first thermal model in which he estimated, if you have a cold slab going down, how quickly does the mantle warm it up. And that is a competition between how fast you can drag the cold material down and how rapidly the heat diffuses in from the sides. And he had a very simple model that essentially was just a layer, and he tilted the layer to make it look like a subduction zone. But he demonstrated, and these are non-dimensional values, but you can think of this as, say, 1300 degrees Celsius or so. He demonstrated that low temperatures could be advected to pretty great depth inside the Earth. And this would have important consequences for seismic wave propagation, the formation of earthquakes, and a variety of other things. So it's a good contribution, even if the model is too simple to be representative of modern subduction zones. A set of influential papers were done by Minier and Tuxes, and I think probably the best one that I found is the one in 1971. Here they improved on the analytical solutions that Mackenzie did by allowing for heat. You may have noticed in this cartoon that, or not in this model, that the only place where the temperature changes is inside the slab. And if heat is diffusing in to warm up the slab, of course the mantle on both sides should get colder. And that's not happening here. And that's because of the assumptions of the boundary conditions and in order to allow for the analytical solution. So Minier and Tuxes set up a code that is a finite difference code where they solved the heat equation, time-dependent variation, the conductive term, and an internal heat generation term. And they created models like this. For those of you familiar with the heat advection diffusion equation, what is missing in here, in that equation? There's an important term missing. You need to speak up if you want me to hear you. I'm getting old. Yeah, there's no advection. There's no advective term. There's no V grad dt or phi dt. The way that they did this was actually to explicitly model advection by taking the temperature at a certain depth level, propagating it a step, diffuse, propagate it step, diffuse, propagate, diffuse. So they kind of got advection in through the back door. This is no. This is not material.
That's the way they're solving it.
Well, in a very approximative manner. Approximative, is that a word? If it isn't, I just made it up. So you can demonstrate that this is not an accurate solution, but it is a good one because it's an improvement over Mackenzie's, because what they did is to allow for the cooling of the mantle on both sides. And they had a simple corner flow solution. There's an analytical solution by Batchelor for isoviscous flow that you can impose. And so this is kind of the first semi-modern idea about subduction zones. This is also an example of an open source code. This got highly popular. Everybody could get this code. I have no idea how they distributed this, whether they just got a bag of punch cards or one of these huge tapes that you see in James Bond movies. But they were very generous with their code, and people used this for a very long time, through the 90s even. Beaudry and Beaudry improved on the numerical solution by not just solving the heat equation with finite differences, but also the Stokes equations. They had an early approximation of a temperature-dependent rheology in there, which you can actually see by the streamlines. Instead of coming in horizontally, you actually get a cold lithosphere, and streamlines go up, focus in the corner, and go down. One contribution they made was to realize that the earlier models did not actually create an arc. Here you have temperatures of 1400 degrees at about 50 kilometers, and that they argued was an arc part. One thing that might look strange is that you have 1400 degrees here, and then this pocket of high heat of 1400 degrees there. That's an artifact of the assumption that they assumed large amounts of viscous dissipation, which is, as I will show you a little bit later, actually an inconsistent assumption in these type of models. But it got closer and closer to nature, closer and closer to what geochemists and geologists saw. Satoru Honda was the first to model a cold corner. I'm very happy with that. Everybody says it's Wada and Wang who invented the cold corner. Well, Satoru Honda did. Sometimes it's humbling how much we repeat ourselves by not necessarily reading older literature. Honda was inspired by a paper by Tatsumi, who's a petrologist in Japan. And this is a cartoon, and look how modern this cartoon is. You know, they have corner flow, 1400 degrees right below the volcanic front, stuff coming up, diapirs, and then I'm not sure that they had flux melting yet, but it kind of got there. And they have this beautiful cold corner, which is imposed by the surface heat flow that was measured accurately in Japan. So the Japanese knew there was a cold corner, and they needed to model it. And Satoru was the first to implement that by just excluding that part of the wedge from the flow. It's very simple. You just say, thou shalt not go here. And he got temperature profiles, which kind of looks like Tatsumi's cartoon, with temperatures of 1400 degrees right below the arc. His heat flow, very low heat flow in the arc. Does anybody want to comment on the magnitude of the heat flow here? Zero seems a little low, yes. Thank you, Jeff. See, Jeff is the only one not shy enough to point out the obvious. This reason why it's zero is that he used an incredibly crude finite difference mesh, and the temperature and the top level and the level below it were exactly the same, so there's zero heat flow coming out of the model. So, but that has to do with the discretization error. I forgot to point out, we looked at the big birds that Christie introduced. Well, here's the Godzilla fish in the Japanese trench. So, Furukawa might have made one of the first models that kind of start looking like what we now call modern day solutions to a wedge. And his argument was to, instead of excluding this cold corner explicitly from the flow, is to say, well, it must have something to do with the coupling between the slab on the one hand and the wedge on the other. And he said, well, if we just, that big bar here is the size of the decoupling zone. If we make that decoupling further and further, then the flow goes up only to that tip, and we naturally create that cold corner. And in the surface heat flow, where he used enough resolution to stay away from zero, although that's pretty darn close at the trench, he argued that maybe decoupling depth of 70 kilometers fits the heat flow observations in these three regions. And 70 kilometers, 80 kilometers, that's pretty equivalent. So 1993 is, I think, when we started seeing some modern work. We made a step backwards with Simon Peacock and Kellen Wang, who wrote a very influential paper in Science in 1999, where they compared the cold Tohoku subduction zone to the warm Nankai subduction zone. And the differences in the contour lines are fairly obvious, with much more spread out, much higher temperatures. Even though you have a cold corner in both of them, the temperature at the southwest Japan slab is much hotter. So we have, and this is now a comparison to phase diagram, including the hydrous melting, the wet solidus that is this curve, where they argued that the southwest Japan slab goes through that hydrous melting, whereas the northeast one does not. This band is simply the temperature at, represents the temperature at the crust and the temperature at the MOHO of the downgoing oceanic crust. There's a huge problem with this model. And what is it? It's in the title. Isoviscous. Why did they, one step forward, two times back, why did they take isoviscous? So I saw Simon present this at a great meeting, a Margins Organized Subduction Factory meeting in Oregon. And I asked Simon, why do you do this? The mantle is not isoviscous. He said, well, it's easier to solve it this way. And I'm only a petrologist. I thought it was funny. So we said, well, why don't we model this with more realism? I said, well, we know Furukawa, so let's do Furukawa and let's model this more accurately. And so we worked together on this, and we wrote a paper in 2002, where we first reproduced, this is always good, you reproduce other people's models, even if you think they're wrong. We first reproduced their existing model. That's the black curves here, with the temperature at the top of the slab and the temperature at the moho. And then we said, well, let's do the Furukawa type coupling, where we create a cold corner rather than by excluding it, we create this cold corner. And we get this green curve for the top of the slab, where we already start seeing that the temperature at this coupling depth increases relatively rapidly at a relatively narrow pressure interval. And that has become a trademark of pretty much all of these models that have a cold corner that's sharply defined, as is suggested by seismology and by heat flow. And then we added Furukawa's trick back in by adding temperature-dependent rheology. We actually just use olivine-style rheology because that's what we think is dominating the deformation of the mantle wedge. And we got the red curve, which, again, we get this very sharp increase, but the temperature gets much higher. And the reason for that is that the higher temperature causes lower viscosity, causes more efficient flow, causes higher temperatures, and there's a feedback until it gets to this equilibrium state. But the higher temperatures are predicted for the top of the slab. And intriguingly, now we predict for northern Japan, which is one of the coldest subduction zones on the planet, that actually the top of the slab can see hydrous melting. And this confirmed a lot of observations that were made because people knew that sediments were melting everywhere. Terry Planck had made a nice database for this, and this met that constraint quite nicely. We also, if we look at the moho temperatures are very low still. So we get huge gradients. This is about 400 degrees temperature difference. Very large, over 7 kilometers, 400 degrees or more. So we get huge temperature gradients in that, and we preserve cold conditions as well. This resolved at that time, outstanding issue. Bill Lehman was a person who studied boron, and he said, boron is coming up in arcs, and therefore slabs are cold. And Terry said, my sediments are melting, therefore slabs are hot. So we had Terry's thorium versus Bill's boron, and they would throw rocks at each other at meetings. And then I talked to them and said, hey guys, we can have it both ways. Terry, Bill, everybody happy. I felt good. It's easy to satisfy or to make a geochemist happy. Well, let me. I'll come back to an example where that did not quite happen the same way. But, so let's move on to a critical test of the accuracy of the solution of these models that we have. And I'm going to use our models because I'm most familiar with them, but it certainly doesn't exclude a lot of work by other people. Kellen Wang, Scott King, Rosa, is that your paper, Magali? Or is this with Manet and Manet? Okay, so. And so there's a large number of people who do these models, and the fact that the models look a little bit similar is because they use similar assumptions. And that's where I immediately want to put the caveat, just because the models look similar doesn't mean that they represent Earth physics. So there's room for debate in all of this. So we're taking this very complex cartoon, and we're simplifying it to this horrible, 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 horrible geometry. We have Peter Kellerman to thank for this. Peter, if you're watching, thank you. We had a meeting after that margins meeting in 2000 in Oregon. We said, well, let's talk about how do we model thermal structure. Got a bunch of people together in Michigan. And Peter said, this is the benchmark we need to do. Fixed 5 centimeter velocity, very realistic constant dip. I guess Doug had a constant dip in his Tonga thing, so maybe this looks like Tonga in that regard. Thin overriding plate, and then a wedge that we assumed first isoviscous, just to look at older models, and then we introduced more realistic olivine diffusion and dislocation creep. Very simple model. And we made a benchmark that got published in 2008. The time it took between the formulation of this benchmark and the publication was 6 years. I've worked on a few other benchmarks, more in the mantle convection community, and my average time between first formulation and publication is, on the average, 7 years. The reason for this is that people think their code is good and everybody else's code is bad. And if you throw a benchmark at the codes, most of the time we found out that all of our codes are bad. And we need to improve them. And eventually we might get the same answer, at which time you've pissed off everybody Can I say that word? You've annoyed everybody in the community by being pesky and saying, well, we really need to. So don't, if you are a graduate student and you're enthusiastic about modeling, do not develop a benchmark. Let the tenured folks take care of that. It's not worth your time. It takes too much effort and too many people get annoyed at you. There was one, I'm not going to say who it is, one person said, well, they had a really hard time matching this benchmark. And this person said, well, I'm chair, I'm busy, I really don't have time to do benchmarking, I'd rather do science with my models, without benchmarking. And the other thing that they didn't like was that there's a fault right there. This is called the seismogenic zone, or the representation of seismogenic. This person said, well, I do fluid dynamics, and there are no faults in fluid dynamics. Maybe they shouldn't be modeling subduction zones. So here's a very simple set of equations. The top looks very similar to what Thorsten presented. Mass conservation under the assumption that density doesn't change. That's a bit of an odd assumption. Is the assumption of incompressibility, also known as the Boussinesq approximation. But it's a good one. It's a lot of codes can handle this pretty well. This is the balance between essentially the stress forces, the stress gradient, and the pressure gradients that are being set up, where this stress tensor is simply the viscosity times the strain rate tensor. That should all look familiar from what Thorsten presented. This is called the Stokes equation. That's the conservation of momentum equation. This is the conservation of heat equation, an extremely simple form. It's steady state, because that's a simple assumption, and then we can converge to the same answer. It's not appropriate for subduction zones, but for the benchmark it's fine, where we have a balance between the advective heat and the conductive heat over from that side. And then we added the idea that we have a non-Newtonian or dislocation creep rheology for olivine, where we have the typical Arrhenius term and a strain rate dependent term, which makes the equations nonlinear and a bit harder to solve. But we think that this is the realistic rheology for the mantle wedge. Here's the first example of a solution. The benchmark grid was imposed to be down to 600 kilometers, 660 kilometers wide. We set up boundary conditions that people agreed upon, and we get this dipping cold part at 5 centimeters per year. It's about average speed for subduction zone, so we still advect a lot of heat into the subduction zone. We get relatively narrow contour lines right at the wedge, so we see strong gradients in here. And we have a pretty uniform high temperature mantle wedge here. We asked everybody to create a spot temperature to say, well, what is your temperature at 60 kilometers depth? This is 50 kilometers, so this is just, actually it was 64 kilometers, but what is your temperature there? And then some people didn't like spot temperatures. They said we need integral constraints, and so we measured the temperature also along an interval in here. So the results of this, after lots of howling and screaming, are this. This is the temperature at the slab at 60 kilometers depth. My apologies, not 64, 60. And then the temperature of the slab averaged between, in this case, 0 and 210 degrees Celsius. So the temperature in the isoviscous model, and this is just a number to keep in mind for the next 3 minutes, is roughly 390 degrees Celsius, right where kind of we now know the cold fork is. This plot is the measurements that were made in the numerical models as a function of the grid point, near the grid solution near the grid point. This is 1 kilometer, this is 5 kilometer resolution. We have a number of codes indicated by the colored symbols. FE stands for finite element. Finite elements are ones where you can kind of use triangles to mesh out the geometry more accurately than you can with finite differences, which assume that everything is kind of a Cartesian grid. And actually, a dipping, 45-degree dipping slab is actually a little hard to solve in these finite difference methods. And so in general, the finite difference methods fared a little bit more poorly than the finite element methods. So here's my convergence from 5 kilometers all the way to very high resolution of a few hundred meters. This is not hard to do in two-dimensional models. This symbol is from Callan Wang's group. It was Claire Curry who contributed this. They have a very unique way of meshing where they actually have a geometrical series where the grid resolution goes to pretty much 0 in their corner point, and that's why we plotted their one measurement right here. But everything, and that's the good news, everything converges to that particular value, even if some of the finite element and some of the finite difference methods have poorer convergence characteristics. So 390 degrees in this point for isoviscous. We then switch to olivine diffusion creep and olivine dislocation creep. This is again the full grid down to 600 kilometers depth. This is a zoom in on the top 200 kilometers. There's a problem with this model. Because we assume steady state, we actually have very long-term cooling of this lithosphere. We get a lithosphere that goes down all the way to 200 kilometers, which is clearly unrealistic. As a function, we also, because we have still this hot material being brought in, this hot material shoots up in an extremely narrow zone. We don't think that this is realistic, but it is an outcome of the subduction geometry. My recommendation, if you start out modeling, is ignore this subduction zone geometry. Start looking at more modern ways. It's good to do the benchmark, but don't assume that it should go all the way to steady state, because you get this artificial, what's called a viscous belly down to this large depth. If you look at the differences between diffusion creep and dislocation creep, the difference are actually pretty minor. The temperature is slightly different, but what you do see is that you get a lot stronger focusing and much higher temperatures at the slab surface than in isoviscous. And we can quantify that by, again, looking at the convergence test. Yes?
So in figure A, the top right.
Can you use a microphone, please?
In the figure A, top right corner, is that just boundary condition cause the contours converge at the corner? The figure A, top right corner.
This one here? Yeah, that's the boundary condition. There was a simple linear gradient imposed down to mantle temperature here. It's an artificial.
But it's not there for the others.
Well, that's because this is a zoom in. So this only is 230 kilometers or so. So the boundary condition is all the way over in the next room. So here's the caveat: don't use this for any type of model. People still do, but you shouldn't. Excuse me. So we had 380, 390 degrees Celsius. With diffusion creep, we get to 580. Huge increase, about 200 degrees Celsius. And that's just due to the fact that we have a more realistic rheology. If we look at dislocation creep, the temperature is actually slightly lower. You might have somehow expected it was higher, but there's a competition between the lower activation energy for diffusion creep and the stronger strain rate influence. In this case, we had a number of codes that started performing more poorly. For some reason, the Katz and Spiegelman code, which is finite difference, could not handle the diffusion creep. They did a little bit better with the dislocation creep. Convergence characteristics are more poor, except for some of the finite element methods. And Mark Bain had a really good code, because he could, at 5 kilometers, he already got the right answer. Not entirely certain how that happened, but that's what he reported. So, the take-home message from this is if you use high enough resolution where the action is, which is where the boundary layers are, you can resolve the thermal structure for a given set of conditions to within about 1 degree Celsius. And this hopefully answers Sean Wei's question from Monday. How accurate are these models? Well, if you just think about the numerical precision of solving these differential equations, it's about a Kelvin. If you use a grid resolution of about 1 kilometer. In 2D, this is easy these days. Computers are fast enough. We have efficient finite element methods. Not sure you can see this that easily from the back, but this is a type of finite element grid we used in the Syracuse et al. Study from 2010, where we have a grid resolution less than 1 kilometer right in this grid point. And so we think our numerical solutions are accurate for the given set of conditions. That doesn't mean that these solutions are accurate for the subduction zone that we're studying. And the reason for that will be discussed after I introduce the tutorial to you. So, Magali, microphone please.
Can you just remind us on the top, is the black line at where it meets the corner, is that a no-slip boundary? Okay, so can you comment on how it might be different if you actually moved your no-slip boundary all the way to the top?
Yes. So in most of our models, we assume that the crust is not deforming. That's a simple assumption that is incorrect in most subductions. might be approximately correct in a bunch of subduction zones. So this boundary condition is actually no slip, meaning that the velocity is 0. And it means that the velocity corner flow will always be deeper than this part. So in answer to Margali's question, what happens if you move this boundary to the top? Well, it depends. If you have temperature-dependent rheology, you will develop a lithosphere. And this lithosphere typically is deeper than about 50 kilometers. And so because of the high viscosity, this boundary will not move either.
So that's the lithosphere, not the crust.
Well, this is 50 kilometers, so it's kind of in between the lithosphere and the crust.
Yeah.
There's no petrology in these things.
60 kilometers thick, so it can't be the crust.
Yeah, this is a particular. I think this was for the Andes, where it's the thicker crust. But in general, if you have an overriding plate that's not deforming, you will get about the same thing for these models. If you have back arc spreading, then you get entirely different answers. So that's the caveat you want to do. You do not want to apply this necessarily for Tonga. Although the back arc spreading, the effect is probably limited to the upper part of the model and not necessarily to the slab. But that's something that we should evaluate. So the subduction zone thermal model essentially consists of solving a heat advection diffusion equation, a Stokes equation, a mass conservation equation, and then put it all together for the subduction zone geometry that you want. And so in order to model this, we're going to set up a toy problem for you that will have the subduction zone geometry, but will not go to steady state. And so it might look a little bit more realistic. We're going to be using an incredibly, fascinatingly advanced and horribly complicated code for this, which was developed by Cian Wilson. It's called Terra Firma. It's something that does everything you ever wanted in your life if you know how to work it. That's why we hired Cian, so we can actually do this. Cian was kind enough to package up a few of these examples that actually run simply, so you're not going to see what's behind the scenes. It's going to be a black box, unless you're interested in how this is all being done, in which case Cian will be happy to show you more examples and give you more fancy models to play with and give you the paper that is written that shows how this is all being done. The examples we're going to be looking at is a very simple heat diffusion problem. Think of this as a cube of plutonium that's being dropped in an ice bucket. The plutonium has heat production, so it gets nice and hot on the inside. On the outside, it's in contact with ice water, so the temperature is 0. And then you can say, well, we can increase the internal conductivity, or we can increase the heat generation. We can go from plutonium to uranium or to granite or something like that. So a few things that you can do with this. This is a simple solution to the problem where the high temperature in the inside, cold on the outside. There's a few activities you can do. Change the diffusion or conductivity, change the heat production, see what happens. Check whether the problem is linear, meaning whether the differential equation is linear. If you change two parameters in a particular way, do you get the same solution? So those are some things to play with. The second thing we're going to do is essentially a form of corner flow in a simplified geometry. This is called the cavity flow problem. It's a bucket of corn syrup. Claudio will be happy to demonstrate how this is being done in the lab. You have a bucket of corn syrup, you put your hand on it and you move it that direction. And then logically, because you're pulling it, it needs to flow this way. You create a pressure minimum, stuff flows in from the bottom, it has to disappear, and you get this nice little circulation pattern. This is a typical type of benchmark for Stokes problems. And again, we can change the velocity, we can change the resolution, we can change the boundary conditions. In this case, you see the fluid moving at the bottom. That's called a free slip. The fluid is allowed to move. You can make this rigid and see what happens. Those are just some things to play with. These are toy problems, but they give you an idea about how we solve differential equations, what the solutions look like, and how they vary. Then finally, we're going to set up a simple subduction zone problem. As I promised, it's the subduction geometry, except it's time dependent, so this viscous belly does not deform. We do have a fairly rigid overriding plate. And because of the temperature dependence, we get a strong focusing, high temperatures at the slab. And the two things that I would recommend we do as a group, these models will run, depending on your computer, for a few minutes to maybe 12 minutes or so. So you won't be able to run thousands of these models. But I think as a group, what we should do is just to look at, as a function of the forcing parameters, how fast is the slab going, what is the age of the incoming plate, how does the temperature at the slab surface change. So here's the temperature at the slab surface. Notice the pressure or depth is going down, so we have a slightly different curve than what we're normally looking at. Or we can look at the temperature below the arc. to see if the petrology of arc volcanoes is represented by these models, where we have, at the surface, we have a low temperature. In the mantle wedge corner, we have the highest temperature. And then right at the slab surface, we have a kind of intermediate temperature before we get to the core of the slab. And so we can take a few spot measurements and see how that varies as a function of convergence rate and speed. And that's probably all we're going to have time for that. Important to note, this is a toy model. I do not recommend that you try to apply this to your favorite subduction zone. If you're interested in a particular subduction zone and you want to have a thermal model for it, talk to me, talk to Ikuko, talk to Scott King, Ikuko Wada. Everybody will be happy to work with you. But I think there's sufficient complications in this that if you just have this tutorial, you probably don't want to apply it. It's like giving me a mass spectrometer and saying this is how you do one measurement. And now, good luck. The mass spec will be destroyed and science will be done a disservice. So moving on to our more realistic, what I think is right now the current state of doing these thermal models, at least in 2D. I'll talk a little bit about what happens with 3D. We have the steady state heat equation. What we need to do is to make this time dependent. So here we have the total derivative, the time dependent term, the advective term. Diffusion, in this case, there's the important assumption of constant diffusivity here. And then a heat generation term. The heat generation term has been abused in these models. An important source of heat that is perfectly appropriate in these models is radiogenic heating in particularly the continental crust. Maybe a little bit in the oceanic crust, but that tends to be not very important. People have also added viscous dissipation, heat due to phase changes, shear heating along the seismogenic zone. Those are all caused by compression. They're all caused by the inefficiency of converting heat into mechanical work and a variety of other things. And this idea of compression is not in these type of models. And therefore you should really not be using that. If you have tidal dissipation and you think it's important, you can use that because that's not part of the equations. It's an external heat source. So my apologies for this long list, but since this talk will be distributed, I wanted to put some words on that. It's important to realize that you should not use shear heating, viscous dissipation, or anything in these type of models. The real problem with this is that in order to do this accurately, you need to use something like what's called the extended Boussinesq approximation. Magali introduced it in her models. Or preferably you go to fully compressible convection, which is a little bit more work, but it's certainly more accurate. This is when you can add these viscous dissipation things in there. If you don't actually move this way, you're creating heat sources in the problem that do not have a fundamental source. So you're forcing heat into the system that doesn't have a complement, and you're violating the heat conservation equation. Doesn't mean that people haven't done it. Actually, we ourselves are guilty of this, but there's a problem with it. Nevertheless, I think it's okay if you know the caveats, and you can see this as a perturbation problem rather than that it's a full, accurate solution. You can probably look at things like shear heating that might happen along the seismogenic zone and see what the effects are. Shear heating itself is relatively easily described. It's the stress that's along the fault times the velocity with which the fault is moving. So this is just simply rubbing your hands together, and it gets warm. Shear heating. The faster you move it, the hotter it gets. If you get a few people that put your hands together and you're strong enough to overcome that, your hands will get hotter faster. This is not a great way of staying warm in the winter because you get tired, you stop being warm, and you die. You really need to have a heat source. The heat source that's being provided is the mechanical work you're doing on your hands. And that's, in this formulation, not actually included. A slightly different formulation, which probably is support, introduces a depth dependent of the shear heating. It assumes that there's some effective friction coefficient times the hydrostatic pressure, which increases with depth, times this velocity. And so you have a shear heating that increases with depth. Jeff?
So I think I get what you're saying, but can you explain a little bit how the problem has to do with compression and what's essentially a shear? There's a mechanism that you're doing work in shear, but
both shear heating and viscous dissipation, where viscous dissipation is distributed, is essentially an expression of the inefficiency of converting heat into mechanical work. It is the second law of thermodynamics. The Boussinesq assumption is ignorant of the second law of thermodynamics. It's satisfied the first law of dynamics, but it assumes that entropy stays constant. So the byproduct of the inefficiency of heat generation is this friction, which is, among others, that stuff that moves causes friction and therefore heating. And this heating is the byproduct of this inefficiency, that's Carnot engine efficiency that you have there. So there's mechanical work that's being converted into heat, which actually is not in the equations, and that's where the problem rises. And that's true for shear heating, it's true for viscous dissipation. With the, please go ahead.
Why do you say inefficient? You said a couple of times that these are it's an inefficient way to generate heat.
Well, it's a heat engine. Heat engines are inefficient.
But you
cannot convert all the thermal heat into mechanical work. There's always dissipative loss.
Right. But
and and there's an inefficiency that is the Carnot engine efficiency.
I guess you seem to be implying that it's very inefficient, or maybe I've misunderstood.
No. In the Boussinesq assumption, and maybe this goes into thermodynamics and the like, that maybe we should move off to later. The Boussinesq assumption assumes that the heat engine is 100% efficient, and that's a wrong assumption. But for some reason, we've been able to use it for a long time.
So
another way that you could think about this is by saying the pressure work which is missing in this problem is exactly what balances the viscous dissipation. So if you toss away the pressure work, you have to then toss away the viscous work. And so that's where the compression comes in, really. It's not so much that the shear heating or the viscous is a compressional problem. It's just that the work done by things compressing and uncompressing as they move through the gravity field exactly balance the viscous heating, essentially. And so if you include one, you include the other. If you don't include one, you have to exclude both.
Yeah, so I had a question which directly follows on that, I think, which is then, so if you were to include these things in a model that isn't an extended Boussinesq approximation or a fully compressible code, what happens?
Well, you're violating the heat balance.
Right, but what do we see in those models if we were to do?
You get more heat where there shouldn't be.
Higher. Yeah. They're too hot.
Yeah.
Okay.
All viscous dissipation, shear heating leads to higher temperatures.
Yeah. Okay.
Yeah. So can we move this off to discussion at the end? Because there's more that I want to present, and this is a highly technical discussion that I think is incredibly relevant if you're doing mantle convection or you're interpreting mantle convection problems. But it probably requires a discussion that's a little bit longer than a few minutes. There's of course a feedback in shear heating. People have been looking for shear heating all over the place. It's the geologist's favorite way of creating extra heat. There's papers all over the place. People said the San Andreas fault, earthquake, heat, and then Lachenbruch came along. His name is Laughing Brook in German. It's great. Lachenbruch came along, and he said there is no heat expression along the San Andreas fault. I poked it with heat flow probes, and there's no heat flow. It's a real problem. Shear heating should exist, but it doesn't seem to do very much. In part, it's, I think, because there's a self-limiting property in this. This shear stress is dependent on the temperature, the local conditions, the viscosity. And the higher the temperature gets, the lower the stress becomes. And so there's this self-limit in there. If you rub your hands fast enough, they melt, and you stop having the efficiency. So you can think of it that way. So this was the conclusion from the benchmark and from internal tests that you can do with these type of things. We can be accurate to be within 1 Kelvin. I don't think that the numerical accuracy is an issue in most of these models, assuming people use high enough grid resolution. But, and this is where you go to applications, do these models represent a subduction environment? And I would say that they have a reasonable first order approximation, but you need to be careful when you're interpreting this for certain things. And the kind of edit, and this is a long table for you to chew over. These are my estimates for what are the most important things that we do not take into account. Do they have a global or a local effect? And what is the approximate temperature difference that you expect as that? This is not an accurate estimate. It's a ballpark estimate that I made based on my experience with these models. And other people might put different numbers on there. I put primary and secondary down, basically divided by the fact that the primary ones might have 100 Kelvin or more, and the secondary ones do not. A very important one is melt migration. As soon as you create melt in the hot mantle wedge, it goes up, it brings up a lot of heat. And this can be locally below the arc, hundreds of degrees Celsius. We do not take that into account, so you do not want to, without taking this into account, compare petrological temperatures necessarily to these models. As we already discussed, back arc spreading is not there. This has a huge effect shallow because you have an arc, there's low temperature at the top. That's a few hundred.
But there are models that include back arc spreading.
Yes,
right?
but I'm going to
James?
self-evaluate my model, so
Right.
yes, you. There are ways
So
to.
we
there-
should throw away your models.
Oh,
no, I'm just kidding.
Yes. By the end of this talk, everybody will have that wish. People do melt migration. So you can do these. It's just that in the models that I'm using, that I'm going to compare to observations, we're not doing it. So I'm trying to be honest here, Doug.
Commendable.
An honest geodynamicist. That's almost as good as an honest
Really?
lawyer. Yeah. 3D flow effects. This needs to be further evaluated. If you have an edge of a slab, there will be toroidal flow. It will locally likely increase the temperatures. We evaluated this in the paper. We estimated that the temperatures could be about 100 Kelvin. If slab velocities of the wedge are as high as what Margaret and Magali are estimating for Alaska, the effects will be bigger.
Are these plus or minus temperatures, or are these plus?
Oh.
Or they're just saying they're variable?
Depends. I
by-
mean, this is melt migration. It takes heat from deeper down and produces more shallowly. So shallow heats up.
Right.
Back arc shallow heats up. Sorry, time depends on forcing parameter. I completely skipped that. This will have a global effect, which could be cooling or warming. The Nankai subduction zone, for example, at this present day, it's moving relatively fast. For a long while, it was moving very slowly, and that changes the thermal structure. 3D flow effects. A long slab edge will increase the temperature compared to the 2D models. Rheology of the mantle wedge and wedge buoyancy. Magali, as part of her PhD work, demonstrated that in order to explain the geoid over the Tonga subduction zone, you need relatively low viscosity and convection. That will change the thermal structure. The mantle rheology itself, we assume a simple dry olivine rheology. There's magma going through, there's fluids. Who knows what the effects are on rheology? And actually, I think the rheologists don't know what the effect is on rheology. So we take a simple assumption, see if it works. But clearly, this needs changes. And I cannot estimate what this error is, but I suspect it's going to be big. Finally, radiogenic heating. If you do not include it, you're missing out on an important source in the crust that could be 100 Kelvin or thereabouts. Also different assumptions. If you have a thick crust like in the Altiplano or a thin crust in the EG&C, if you use the same model, you make errors. Secondary, fluid flow in the slab. I hope I convinced you that fluids that are generated by the breakdown of mineral dehydration or by mineral dehydration reaction, that they partly flow up the slab. The amount of fluid and their heat capacity is relatively low. So there is an effect, but I don't think it's huge. Shear heating, I think, is low. I'll be happy to talk with anybody after this. We've actually started evaluating this, and together with Callan Wang, 50K is probably the maximum you can do in the crust compared to models without shear heating. So 50K is not unimportant, but it's, I think, secondary. Phase changes, those have only local effects. You cannot include them because it's part of this compression cycle, but estimates are that they are a few tenths of degrees Celsius, so they're really secondary. Please.
There have been several studies about the shear heating, and considering the transition between brittle ductile transitions and phase transitions, and there are actually studies showing that shear heating can cause pseudo-tachyte formation, and change of temperature is far greater than 50 K. Several hundred degree K has been.
The pseudotachylites are also this big. The pseudotachylites are also this big. Maybe this big? Has anybody seen one bigger than this? That means that you have a few centimeters of very high shear heating. This heat diffuses out over a much larger surface, and therefore the total effect on the crust is much, much lower. So you are correct that locally the effects can be higher, but if you are comparing this to, say, an eclogite that is sitting 500 meters away from the pseudotachyllite, the thermal effect will be very small. So that's important to keep in mind with this.
Yes, but there are numerical studies showing the including brittle ductile transition in the heating. That is.
I totally agree with you, but this is an incredibly local effect on the centimeter scale, which is
in the study I remember it caused several kilometers of change in temperature.
We can look at that. Okay. So this is it. My scientific reputation, and after the next 35 minutes, is going to go completely out of the window. Because I'm going to do something very dangerous. I'm going to compare our models to observations. Al Gore called this the inconvenient truth. Background is for Cirrus. This is a very nice outcrop of metavolcanics in marble. We have places where subduction zone melanges come to the surface, and we can take a look at them. And you guys are going to be doing that on Saturday in the Tiburon. So we can learn a variety of things from that. So I'm not just going to look at rocks. I'm going to look at a whole bunch of other things. Just to say that we satisfy heat flow approximately. This is a model from 2012, which is very similar to the Syracuse model of the Tohoku subduction zone, where we specifically focused on the temperature in the earthquakes. Our heat flow prediction is in this line. The measurements are in the dots. We've scattered high and low heat flow over most of Japan in the back arc, and then we have this famous indication of cold corner. And actually, our heat flow might be even a little bit high for this region. And that's actually not uncommon. Our models actually have a hard time creating the cold conditions that are suggested by the heat flow. The models I'll be discussing are based on a project that Ellen Syracuse did. She was a graduate student with Jeff Abers at Boston University at the time. And she, at some point, said, "Hey, Peter, I got these new slab services, and can I write a chapter in my thesis that uses some of your geodynamical models for this?" I said, "Sure, come on over." We spent a week, and we had a suite of subduction zone models. And I thought it was just going to be a chapter in a PhD thesis, but we decided to submit it to PEPI, and it has gotten some traction, which I was very happy about. In a way, this is a CIDR project. It was not inspired by CIDR, but it takes seismology, it takes geodynamics, combines the two, and it tries to improve our common understanding based on the combination of the disciplines. What we did, or what Ellen did, was to take sections of various subduction zones that are relatively mature, so we don't do the Macron subduction zone, for example, because that's in a continental collision stage. And we took about 800 kilometer segments and then made an average slab geometry. So none of the slab geometries are perfect for any of these geometries. They're kind of averages. But because it's for all the active arcs, it provides a global estimate. And so people have liked to cite this because they say, well, this is my subduction zone, so I can use it. Or people said, well, I can take the global average and then make decisions about whether it makes sense. Or we use this to measure or to predict how much water goes into deeper mantle, for example, because we have global estimates. Here's some simple examples of the temperature distribution. And I'm going to be focusing on a hot arc, which has low velocity of low convergence of young oceanic lithosphere, Tohoku, fast convergence of old lithosphere, and then Nicaragua kind of in between. This is down to about 230 kilometers. Notice that the horizontal axis is stretched just to make these pictures fit on the screen. They don't all dip in the same way. Cascadia, you lose the blues very quickly, and a very warm slab at depth. Nicaragua, you see the blues go a bit further. For Tohoku, you advect this cold temperature to very large depth. So you have between three subduction zones, which are, two of them are end members, very large temperature differences predicted in otherwise the same geometry. This is the temperature at 120 kilometers depth at the slab surface. And it's plotted as a function of the thermal parameter, which is simply the speed, the convergence velocity, convergence speed, times the age of the incoming lithosphere. The older a slab is, the colder it is, the faster it goes, the colder it is. And therefore, you have warm subduction with low thermal parameter, fast subduction. So we have Cascadia over here, Tonga over there, and then Nicaragua and Tohoku are also indicated. Yes, microphone, please.
Can you just go back to the previous slide and explain how those different thermal structures came to be? So you had those initial geometries, and then they're warming. I guess you had initial temperatures or something, or maybe just it might be useful for sort of people here. Like, how is it that they all have these different end temperatures that you're using?
What we did in these, thank you, that's a good clarification. What we did was to start off with an overriding plate that was appropriate for whether it's oceanic or continental, and then the initial thermal structure of the age of the incoming plate. Then the boundary conditions, we kept the age constant here, and we just started advecting it, so it's a time-dependent process. And for most subduction zone, after about 20 million years, they've reached what you could call a quasi-steady state. If you evolve it longer, typically the lithosphere starts cooling further and further and further. So it's not a full steady state, but it's a quasi-steady state because the temperature structure in the slab doesn't change anymore. And that was the focus of our study. For the slowest subduction zones, like for example Cascadia, we evolved it for a little bit longer. For Nankai, because it only has been active for 17 million years, we only evolved it for 17 million years. But these models are, you can think of them as approximating steady state for the slab and the wet structure.
Peter, in all those models, the slab is cold or warm and young or older, but the angle of subduction is always the same.
Yeah, like I said, notice that the horizontal axis is different for all of these figures. So they're stretched. And that was just to put them together on a screen. So the subduction slab is definitely not the same, or the subduction angle is not the same for all these three. Yeah, the clarification is we used Allen's slab geometry, which was an improvement over previous models based on better interpretation of teleseismic records.
So Peter, how are these models that you used for those computations different in principle from the toy model you're going to do in the tutorial? And then my other question is, when you look at the next slide, you have this scatter around the thermal parameter. And given that those are numerical models, I wonder where the scatter comes from. I could see how, you have a systematic deviation because there's different physics in there besides pulling down the isotherm, and you have geometrical complexities. But it seems like
you're answering your own question.
That's it.
Yeah.
Just the geometry.
Yeah, pretty much. The big difference between the toy geometry of the constant dip slab is the fact that we have a realistic slab which starts out shallow and then deepens. And the geometries are different and the pathways that they arrive. The thermal parameter technically, and I did not include it in this graph because if you have a variable dip, I don't know what the dip is, but a lot of people like to put the sign of the dip in the thermal parameter. And, so there's a little bit of scatter, but actually, particularly if you think about the temperature of the sediments and top of the oceanic crust, where sediment thickness varies from subduction zone to subduction zone, so that's another thing that explains scatter. The average temperature is about 900 degrees Celsius at 120 kilometers depth. And the variations are up to 1,000 down to 800. So the slab surface temperatures tend to be uniformly quite hot. And that's due to the non-Newtonian rheology and temperature-dependent rheology. If you go down to the bottom of the oceanic crust, it's always assumed to be 7 kilometers from the top of the oceanic crust, you got a much larger scatter. And much bigger differences, down to about 300 degrees for Tonga, whereas Cascadia is actually not that much different from the top of the slab. This is an important graph. If you are used to looking at top of the slab temperatures, keep this graph in mind, because the crust is not the top of the slab. The crust is a 7-kilometer thick entity, and you have huge temperature variations in there. You can preserve in Tonga, and this goes back to the Bill Lehman versus Terry Planck argument, you can preserve low temperatures at the MOHO when the top of the slab is hot.
Peter, so how important is, there is a slight variation in crustal thickness. Is that going to be important? Like if you have 5-kilometer crust versus 7-kilometer crust?
Yes. But
just thinking in terms of...
We assume 7 kilometers to keep it simple. There are variations, yes, and you can get our models and take a look. These models are available. Anybody who wants them can use them. So, and this is where the dangerous part starts. I'm preparing a paper, and I looked at who cited our paper for reasonable reason, not to say, well, the Isobunin trench is moving at this speed, which you can look up elsewhere. And so we inspired a whole bunch of geochemical work. This is where people took our models and then did geochemical modeling, for example. We have a bunch of people who did geophysical work, again doing the same thing. They put our temperature profiles on top of an electromagnetic profile and said, hey, everything looks good. We inspired increasing amount of experimental work where people said, well, Syracuse et al. Predict that the slab temperature is in this range, therefore our experiment should be at this pressure and temperature. If we are wrong, we have contaminated the literature for decades to come. So let's see how wrong we are. Oh, I told you this was going to be fun. We have a serious problem, and that has to do with the fact that our models logically are not perfect, and sometimes they're too hot, sometimes they're too cold, but sometimes they are. Oh, come on. Audience participation, people. I know it's only 10 o'clock and you want your coffee, but we have a Goldilocks problem. So let's start with the just right, because that makes me feel good. Important assumptions, just to quickly go through this. This might be the important slide to keep in mind when you're comparing these observations, because the observations may not be applicable. The model may not be applicable to the observations you're trying to solve. Models are 2D. Don't use these models if there's 3D geometry issues. We do fixed forcing parameters, meaning we do not change the velocity, we do not change the age of the incoming plate. We assume an 80-kilometer cold corner everywhere, even though in some cases we know that it could be slightly different. We just did for global consistency. We have a dry olivine composition. No wet, no melting, no nothing. We don't have phase changes, we don't have fluid flow, we don't have magma migration. If your problem involves magma migration, you need to estimate the effects based on this ground model. We have thin overriding plate, which we adjust for whether we have oceanic subduction or continental subduction. And if we have thick continental overriding plate, like in the Altoplano, we adjust for that. As Margaret helped clarify, we do have a time-dependent evolution to this quasi-steady state. We don't have shear heating, we don't have viscous dissipation because I think it's inconsistent. We do have radiogenic heat production where it's appropriate. Mantle potential temperature is kept constant at 1422, actually 1.5 degrees Celsius. This incredibly precise number is based on the GDH1 model by Stein and Stein, which is based on the flattening of the heat flow curve. It's a plate cooling model where they have a temperature of 1450 degrees at the base of the lithosphere. That translates to a potential temperature of this. We know that in some places, like in Tonga, it's hotter. We know in some places it's colder. We did not adjust for that. In general, we have not made individual adjustments just to make the model look better. This is really an attempt at the global average using the same level of assumptions. So keep that in mind as we're going through the observations. This is work by Lauren Cooper and others in Terry Plank and other folk groups, where they developed and tested a new geothermometer that's based on the ratio between water and cerium. And what they argue they can do with this is to measure the temperature under which fluids leave the slab below the arc. And because I'm not a geochemist, I'm going to leave it at that. I'm assuming that they know what they're doing. And what they did was to plot this temperature that they're estimating for a variety of volcanoes or a variety of arcs, Tonga, Kamchatka Aleutians, Guatemala. IZ is Irazu, it's a volcano on the southern end of the Costa Rica subduction zone. And they plotted that versus, or we plotted our temperature, our predictions versus theirs. And if they at some point would have suggested that the average temperature below the arc is 800 degrees Celsius at the slab surface, I would have been incredibly happy. They even get something that looks like a correlation, which is even better. Temperature differences for the black ones, which is where they use the regression curve for, is less than 50 Kelvin. Cascadia and Nicaragua are a little bit bigger. The biggest difference is for Irazu. I think that this is an example where you have a 3D slab effect because you're sitting at the edge, and the actual slab temperature is much higher than what we're predicting in a two-dimensional model. Microphone, Doug.
Yes, so...
Microphone, please.
So when they did this this study, were there constraints on the temperature entirely independent of your model, or did they calibrate it relative to the model?
I hope it was totally independent.
They're independent.
Can we move on, Matt, because we're starting to run out of time. Here's another, and so here are a couple of papers that are listed that suggest that we're right on. Here's another example. These are diagrams. They're exploded crust models of the metamorphic facies, green schist, blue schist, eclogite, Hey, for warm subduction zones, we get amphibolite. You all know this one now. And what we can do from that, use perplex, we can estimate the water amount. This is the important graph, that's why there's a circle in there. We predict that this is 80 kilometers below the, or with slab depth, this is 100 kilometers. We predict, in 2011, we predicted that the only water source for the Cascade volcanoes would be from the peridotite. And then, Paul Wallace had a very smart graduate student called Christina Walowski, and she wrote 2 beautiful papers, one based on deuterium and one based on boron isotope ratios. And in both cases, I just put the title up, but in both cases, there's convincing arguments made that yes, the fluids do come from the mantle section. It's always nice when geochemists come to the rescue. Thank you, Paul. So this is what we have. This is the big bird. This is the Sesame Street model of a subduction zone. Oh. Not all my jokes are funny, I guess. So we have constraints on the peridotite below the crust. We have constraints on the top of the crust. And then let's see what else we can do with these things. There's a large literature where I classified as the authors think that our models work. That's a highly non-quantitative statement. And I use this based on what the author said. If the author said our results are consistent with numerical models or vice versa, I say this works. And that means that temperature differences could be 100 degrees or so, but the general trends are the same. And to illustrate that with 2 examples, which are from exhumed record. This is a paper by Erdmann and Lee, where they used literature data for lawsonite eclogites and continental crust fragments. They only did continental crust above the coesite quartz boundary, which is a standard definition, a standard boundary between high pressure rocks and ultra high pressure rocks. It's commonly known that lawsonite eclogites really do not get exhumed further than when they were at 80 kilometers depth. Continental fragments come much deeper up, and that might be logical because they have the buoyancy. If subduction stops, they have the buoyancy to pop back up. And intriguingly enough, it seems there's an offset between these groups that matches this low temperature to high temperature increase. So there's a suggestion from the literature data that at 80 kilometers depth is not just this quartz coesite, but it's also this coupling depth that is represented in the metamorphic rock record as predicted by us. This is a model for Irazu, which is not the coldest on the planet, and this is Cascadia, which is one of the warmest on the planet. And so we have intermediate to hot conditions for these rocks. There's a paper by Donna Whitney, which essentially does the same thing, except she's one of those geologists that thinks that pressure goes down, which is correct. So it's, you need to turn your head upside down if you used to think of pressure up. And she made a compilation of our temperature conditions, which are, in this case, normal to cold. Not entirely certain why she did that. And then looked at lawsonite eclogite localities. There's Guatemala, there's Australia. And then her favorite exhumed terrain is in Turkey. I cannot pronounce it, but it starts with an S and has a V in it. Which she says is the highest pressure lawsonite eclogite locality. And in order to make this impressive, she calls this the point of no return. I love petrology. There's the forbidden zone. And now with the point of no return. I can see a Monty Python movie staffed by petrologists. You have reached the forbidden zone. Thou shalt not return. And you're thrown off the bridge. There's one weird example. I don't know anything about this rock. Maybe you guys do. It's in Arizona. It's a xenolith that has lawsonite. There's a couple of rocks with lawsonite pseudomorphs, and there's a couple of continental fragments. But she argues, like other people do, that lawsonite eclogite, which is characteristic of mafic lithology, oceanic crust going down, is not exhumed beyond depths of 80 kilometers. Here's some work by Gray Beebout's group for alpine lawsonite eclogites. Again, notice they stop right at about 3 GPa, about 80 kilometers. And their trend parallels nicely the trend that we predict in the forearc. So this is what I would call it works. And now we get to the places where people say it doesn't work. We made a compilation ourselves, and Sarah discussed her work on this, where it turns out that if you look at a global compilation of forearc exhumed rocks, they don't match our models at all. That's too cold below the forearc. To make things fun, there are people that argue that our models are not warm enough, or not cold enough below the forearc, they're too warm. You can't make anybody happy these days. And then there's a large literature that talks, not a reasonable large literature that says we're too cold below the arc. And I think there's some reasonable reasons for this. I cannot explain the top one. The other ones I think are reasonably explained. So let's start with this global compilation. This is ours. This is work. I talked to Simon Wallace and his student Endo put together a global compilation of exhumed rocks, which may be directly related to subduction, up to about 2.5 GPa. So this includes continental fragments, but also loss and eclogite, things like that. Our models match only for the intermediate temperature to the warm temperature. We have a large suite of models that are much colder than those exhumed terrains. And this is not just a minor difference. This is a few hundred degrees. Sarah in the paper took our models, took the global average of those, and then compared them to the global average from her exhumed rocks. You can do that, but it's meaningful is another question. We can discuss that. And so she argues that our models are too cold by 300 degrees. That's enormous. That's worse than magma migration. It's almost as bad as pseudotectilites, but this is over the entire crust. So this is a problem. How do we solve this? And so in pre-CIDR days, what we would have done is to say, well, us modelers, we don't know what to do with the rocks. Let's just ignore them. The metamorphic petrologists could have said, well, the models are clearly wrong, don't use them. But in CIDR days, I think it's more constructive to see this as an instant conflict. That must be a solution. And that requires us to talk to each other and understand what the assumptions are that go into these models. And I'm going to talk about the assumptions that go into our models, because I'm not a metamorphic petrologist, and I assume that everybody who does these compilations know what they're doing. So, at face value, our models are much too cold in the forearc. Notice that it's only in the forearc. Once we get to the past the forearc, we're okay. So the continental fragments are just spot on. It is that forearc that's the problem. And I don't know what to do with this. Our models cannot logically be adjusted to create these forearc conditions. We just cannot do it. The reason for it is that the heat flow tells us the forearc is cold. We cannot increase the temperature by 300 degrees without violating heat flow constraints. There's not a credible heat source. Maybe locally in the pseudotechelite. But on a crustal scale, shear heating may contribute 50, but we need 300. So we cannot make these models. A logical extension of our models, if we throw all caution to the wind and we say we're going to ignore heat flow, we're just going to pump in as much shear heating to increase the temperature, we have a logical problem. Because if we would increase the forearc temperatures to where the rocks say it should be, the arc conditions also increase by that amount, because this extra heat is just happily advected downward. And so then we all of a sudden start violating the metamorphic rock record, as well as Terry's thermobarometer and everybody else's estimates for the metal wedge. So logically, these models are not compatible with the rock record, and we cannot make them compatible. So that means that our models have assumptions that are different from what the rock record does. And in that sense, I think it's useful to think about when rocks get exhumed. It's not like we at present day have a subduction zone where in Japan you can go look at the subduction channel and eclogites are being popped back up. There's one exception, and that's the Marianas and a little bit in Isobonin, where we do have forearc serpentinites that are being squeezed up and come to the Earth's surface as mud diapirs, or mud volcanoes that are diapiric uplifts. This is facilitated by the low density of the serpentinite and the very thin and extended oceanic crust that's in the overrunning plate. But in general, exhumed rocks are rare. They're punctuated. It's a nice paper by Philippe Agar that demonstrates from geology that exhumation is short-lived and tends to happen at the beginning and the end of subduction, as well as kind of in the middle. And his group's suggestion is that we have either warm oceanic crust that's going down that is relatively buoyant and therefore allows for the exhumation. We have continental subduction, where the continental rock is light enough that it will pop back up when subduction ceases. Or we have changes in convergence parameters. For example, the initiation of subduction, the end of subduction, the overriding of a transform fault, a ridge, those type of things. I cannot test number 2 and number 3. Our models do not do continental subduction, and it's actually hard to model. Changes in convergence parameters are not taken into account. And again, this is also hard, particularly the initiation of subduction. We don't even know how subduction initiates, let alone try to model that. So those are hard. What we can do is to test the hypothesis that it's young oceanic lithosphere. There's an attraction to young oceanic lithosphere because it's relatively buoyant. And so if you have hot stuff sitting there, it allows you to bring stuff back up to the surface. So here's a compilation that I put together for Mike Brown, who's also at Maryland, and Tim Jones at Curtin in Australia, where this is yet another metamorphic rock compilation of exhumed terrains, where if we plot for the warmest subduction zones, which are down to 30 million years age of incoming plate, we actually get quite a nice overlap, and again, a suggestion of a shift between the fore-arc and the back-arc temperatures. So if you want to think about this hypothesis test, that in answer to Matt's question, do terrains get preferentially exhumed when they're hotter and younger? Yes, it could be. But there is a problem, and Sarah is absolutely right about this, is that we have these very cold conditions that just don't come back to the Earth's surface. And is that an artifact of our models, or is it because these rocks just disappear and are never seen again? The more I think about it, the more I think we're having an issue that we're comparing fruits, different type of fruits that even although they grow on trees, they're not the same. That's probably what we're looking at here. One of these is easier to, I mean, both of them are healthy for you. One of them is easier to eat without peeling. The other one is better for mimosas. Maybe we're just looking with different measurements to this problem. And what I think the solution for this is, I mean, our models do not exhume rocks. The rocks are gone. Well, they're no rocks, it's a differential equation. But if you think of these paths as being representative of the rock record, they're gone. They're not being exhumed. And so what you really need to do is to develop models that do exhumation. And maybe under those conditions that Philippe argued for. So we need to develop models that go from initiation to maturity to closure. And then see under what conditions we can exhume rocks, which requires buoyancy, and what those temperatures are. And that's a huge challenge, but I think that that's where we're kind of leading this discussion. So I don't have a resolution for the fore-arc temperatures, except the fact that our models are, I don't think, are appropriate to be compared to those, even though I've done it myself. Jeff, microphone, please.
If you were to make a cocktail napkin calculation, just from the advection of material in the exhumation process, what sort of temperature changes might there be simply associated with moving the hotter material up?
It depends how hot it is. So that if it's cold stuff, then the advection is less important. If it's hot stuff, it's more important.
Is there a possibility that you have a fluid channel of hot fluids that exists in the subduction, channel, essentially coming from the deeper, hotter parts, so that these rocks are not sort of representative of the gross?
Yeah, we tested that explicitly using Cian's fluid flow models, and it's completely secondary. So there's not enough fluids to go around, and they don't carry enough heat. So to move on to people who complain that our models are too warm, and they've got an interesting argument. This is only for warm subduction zones, by the way, but Glenn Spinelli has written about 20 papers with the same message. I think one of them is probably all you need to read. Cousins and Spinelli is a good one. They argue that if you have young oceanic crust, that the outer 600 meters of the volcanics is actually very hydrothermal. And as a consequence, hydrothermal fluids cool the oceanic crust. And that's representative by, outside of the trench, you have very high heat flows, which is representative of this heat being sucked out of the young oceanic crust and being pumped into the ocean, which means that the temperature of the oceanic crust should be lower. We do not take this hydrothermal circulation into account. And if we look at our predictions for a very detailed model of this Cascadian margin, our heat flow measurements are, well, roughly 20 milliwatts per square meter too hot for this hot margin. So that's an interesting problem. We've reproduced, if you do the hydrothermal circulation, we can match the heat flow. So I think their argument is sound. It's only for the warmest subduction zones, down to about 30 million years. But this makes the problem even worse. I mean, our warm subduction zones are even colder if we take this into account. It's going to be the last comparison. Few people have looked at our temperatures and said, you're too cold below the arc. Here's a paper of my good friend Simon Turner, or from Simon Turner's group, where they looked at the back arc in the Tonga subduction zone. And they also used this water cerium thermometer to essentially estimate what the slab temperature was, which are the symbols here. And they compared that to our predicted model for Tonga. And the difference is about 100 degrees, where we are too cold. In this case, I feel comfortable with this to argue. It would be nice to set up a model, but since we're in Tonga, we have rapid retreat, there should be a relatively strong toroidal component and bringing in flow into it. We also have this huge hotspot. That's Matt's favorite hotspot, I think, because it's an island where you get drinks with little umbrellas in it. So that this arc is warmer. If it was colder, I would have been perturbed, but it's warmer. Cian might also argue that the potential temperature in this region is hotter than that in our models, although it's not by that much. Here's another example, same idea from Esteban Gazel's group. They looked at the Calabria arc, which is a really pathetic little arc. It's the last little bit that goes down after all this massive Tethys subduction. Our prediction for this is the solid blue curve. They see evidence for sediment, wet sediment melting, so they say you need to increase the temperature by about 50 to 100 degrees. And again, I think it's reasonable, and they interpret that in their paper, that due to the slab rollback, there's just hotter material coming in through the side, which is not represented in our 2D models. Our models do predict melting. This is just an internal test. Underneath the arc, we get high temperatures, not hot enough for dry melting, but you add a little bit of water, you reduce the Hirschman solidus by a little bit, and you create a nice little melt pocket. So that's at least an internal consistency check on that. So back to our cartoon picture, we have a number of places where we have measurements that tell us something about the validity of these models. It's been argued for a long time by people who look at arc volcanoes and the melt products in them that say, well, it might be nice if you get melting, but we see equilibration of melts at the Moho at about 40 kilometers depth, and your temperatures are much, much lower. They should be well over 1,000 degrees Celsius, and yours are below it, and so your models are not accurate. That's correct, and a large part, I think, that is because we do not take melt migration into account. So I was heartened by Adam's cartoon, where he has, he doesn't have a cold corner, but it's okay. You get melting at depth in the corner, and then you have this submantle lithosphere that's being penetrated, and then at the lower crust you get this mash hot zone that then eventually leads up to, so there should be magma transport from the bottom of the lithosphere into the bottom of the crust. So we can quantify this a little bit. Here's a paper from Paul Wallace's group where there's experimentally determined temperatures of last equilibration, which all sit at about 1,200 degrees Celsius or so, right at the Moho. If you look at the thermodynamic model or the convection models, none of them have these high temperatures. But of course, we have plenty of heat below it. So what do you need to do to go from this to that?
Move melt.
Move melt, okay, so let's move melt. I'm gonna move melt. Watch me move melt. Ha! It's that simple, I think. So there's the yellow arrow. Now, this is a cartoon, so can we quantify this a little bit better? Here's a recent review paper by Christie, an American mineralogist. Just came out, or is about to come out.
It's out.
Here, this is upside down. Pressure now goes up instead of down. Those are the kind of constraints from petrology about what the temperature of the magmas near the Moho should be. These are the center of the mantle wedge, high temperatures, but at relatively high pressure. And again, those are my simple pathways I can sketch in. There's an interesting paper by Peter Kellerman from 2003. Peter and I go back and forth on this. He actually created a solid state model that elevated the temperatures right at the Moho to be as high as constraining the petrology Was nice for the petrology, except that this arc is where the slab is at 50 kilometers depth, which is not in agreement with anything we know, and the heat flow was slightly violated. And it's a good thing that heat flow doesn't care about being violated, because it's not very sensitive to people's criticism. To quantify, I had hoped that Cian and Mark Spiegelman and I would do this at some point, to actually quantify what the magnitude is of the temperature increase at depth. And so here's a cartoon. This is not a model. This is a cartoon from Rich Katz and Phil England in a Nature paper, where they say, well, we create this melt here, and then of course it channels up towards the arc. There's a preprint, and because it's a preprint of a student, I'm not going to put the link in, but you can find it, or I'd be happy to point you to it, which does actually the full fluid migration model and suggests that the temperature increases about 300 degrees at the MOHO, which is roughly what the difference is between the petrological and the thermal model estimates. So there's hope. And again, we have conflicts between models and observations. We look at it, we say, could this be the solution? And then you find new ways of looking at that. So that will bring me to my last slide. As was clear from the 50 years of thermal models, we've seen a big evolution. No doubt in the next 10, 20 years, we're going to see further evolution. And what I presented as the current state is going to change. And improvements that I hope we will be able to make is to integrate the thermal predictions with fully dynamic models. This has been hard because dynamic models have a will of their own. They don't always look like Tonga or Cascadia, but we can try. We certainly need to improve rheology. I feel comfortable enough with the mantle wedge rheology because the temperatures seem to be reasonable, and therefore the rheology is probably reasonable. But we have a large amount of work to do with low temperature creep mechanisms, particularly below about 800 degrees Celsius, where things like wireless creep start taking over, grain boundary sliding, and all sorts of other processes that we currently do not take into account in our models. Of course, 3D, increasing number of people publish 3D models and say, well, how does this differ from 2D? We have a paper from 2012. Ikuko Wada has been producing these as well. Evolutionary models, I think, are important, particularly to look at the rock record and see if we can find better comparisons there. Fluid and melt migration is an obvious target. We got one paper with Cian Wilson, where, again, this is the fluid being channeled up. Doesn't have a huge thermal effect, but it has an important dynamical effect of lubricating the crust and therefore likely causing earthquakes. And then, obviously, we need to evaluate these models with observations. And I don't think you should be afraid of conflict. If you compare A versus B, you don't necessarily get the same answer. If you always get the same answer, you might be looking at a boring problem. If you get divergent answers, that's where the excitement sits. Uncertainty and tension drives discovery. And particularly from a CIDR perspective, I think it can be fun to look at these uncertainties. Even though you might not get as much funding if you produce something that is an uncertain hypothesis, but it's certainly fun to do that. I think it's okay. We can be creative. And I was heartened on my walk in this morning. I saw this sculpture that was definitely created under a lot of tension. This is on the west side of campus. So clearly somebody thought really hard about subduction zones and could not handle it anymore. So with that, any questions or answers?
Thank you. I was just wondering about your first example where your model worked, that the geochemical data were like from volcanic areas. So shouldn't it be hotter than your model prediction? Because you said that if you have melt included, you underestimate the temperature. So my question is, why did it work?
It's because it's not melt. Ooh, come on, you can do it. Uh-oh. Well, the example of Terry Planck's geobarometer, the water cerium, is the temperature at which the fluids leave the slab. So that's before you create melt. So that is a reasonable match. Also, I would argue that, and it's stuck on this slide, so that's maybe a good point. I would argue that our models are consistent with the magma equilibration temperatures at the MOHO 2. The only thing you need to do is to migrate the fluids. or migrated magmas. So I think we're consistent. The magnitude of the magnitude of the temperatures and the variations therein are perfectly in agreement with the petrology. Not just not the pressure, but that's the fluid path.
So, question here.
Claudio, why don't you do first?
Thank you, Peter. Very nice overview. Excellent. I was just thinking about coming back to the point you made about the fact that the sampling that we have on the geological information about the PT trajectory of rocks we have, exhumed rocks. And I think this is a very important issue, and I agree with Philippe in the sense that we may have a very partial sampling, and maybe for example, when you look at continental exhumed material, it is clear that they often occur, the exhumation during slab rollback. And this has been proven in several sites, like from Mediterranean, Papua New Guinea, or other region, or Norway. So those are the very important region for the observing eclogite or whatever on continental material. All of them occur during either slab rollback or the upper plate moving away from the trench, so making space actually. Mm-hmm. So I was wondering whether this may kind of affect the thermal or may perturb somehow.
Yes, absolutely, because you will bring hotter stuff up by pulling the plates apart, you will bring hotter stuff up. So in a qualitative sense, absolutely. It's just the quantitative models need to be developed to match with this. And that's where since our models do not have any of these mechanisms, they might not be the ideal ones to be compared to the rock record. And so our conditions might just be too cold because we do not take these extra ways of bringing stuff up. There's no subduction channel in these models. There is no exhumation in these models. And so that's why it's an apple and orange type of comparison that I think we should keep in mind when either looking at my own comparison or that of Sarah's. And this is where we need to go to these evolutionary models that actually take the exhumation into account. And of course, Taras Geria has published a few papers, except that if you do this in a steady state subduction environment and you create a subduction channel, you create very high temperature below the forearc, which is inconsistent with modern heat flow. So you need special conditions, I think. And that is consistent with the punctuated nature of the exhumed rock record.
So you showed the result for the intermediate depth earthquake in Japan, and we have intermediate depth earthquake for most of the subduction zones, and you have this diverse thermal models for all the subduction zones. Can you comment on is any first order correlation or connection between their behaviors?
Yeah, the only place, there's only a few places where we have sufficient information about the structure of the subduction zone from, for example, receiver functions to allow us to put the earthquakes in that structure with accuracy. And those places are Japan, of course. Those are the array below central Alaska, the Bear Array. Those are below the Cathay region. What else, Jeff? Nankai, that's Japan. So there's only a few places where we can do this. And the intriguing correlation is, and I hinted at that on Monday, is that there's a petrological control on where the earthquakes occur. In cold subduction zones, they tend to be in the crust, ignoring the lower plane of the double seismic zone. They tend to occur in the oceanic crust. In warm subduction zone, they tend to occur in the mantle. And so that is a very important correlation that indicates that mineralogy and petrology is important in the causes of intermediate depth seismicity. There's a hint that fluids may be important, particularly in the upper plane of cold subduction zones, because the seismicity disappears when eclogization is complete. So those are the correlations we have, but it's based on very limited number of measurements. There's unpublished work yet from a student by Stefan Rondenet in Norway that does a similar study for the Hellenic subduction, Western Hellenic subduction zone, and that's what is intriguing. It's intermediate. It's very old, 190 million year old lithosphere that's going down very, very slowly. So it's a very weird intermediate type of zone, and there they argue that the earthquakes are both in the mantle and the crust, and to kick it all off, also in the mantle wedge. And so it's unpublished work, so I didn't show it, but so there's a lot more to be discovered about these things.
Another student question before we go to more senior participants.
I have a quick question. Do you think serpentinization in the wedge would matter much in terms of heat production? I'm sure it depends a lot on kinetics, but has anyone looked into that and whether that would change things?
In some of the older papers, people threw everything in their models, so they probably did this. I don't know of any modern papers where this has been done. I again suspect that this is relatively secondary. But it might be nice to go beyond hand-waving arguments and actually model this. But you need to do this in a careful environment because these are phase changes, you need fluid migration, you need phase changes, and you need to be careful about violating the heat balance. So sorry I can't give you a clear answer, but I think the effect is relatively minor.
Well, my question follow up actually that, and my question is on the serpentinization in the subducting slab. Whether it takes into account in the models, and would it change how much fraction of serpentinization people use? Yeah, we do not do the thermodynamics of any type of mineral changes in these models. We just predict the temperature, but we do an a posteriori calculation of the mineral phases. And that was these colorful diagrams that had the amphibolite and the blue schist and the eclogite in it. Also had serpentinization, and in the cold subduction zone, the transition to phase A, or the dehydration in warmer subduction zones. Even without dehydration, just the existing of serpentin going down? We just looked at where these phases are stable. And then we argue that the changes that occur are the places of dehydration, the places of fluid production, and then we take those fluid production things and look at fluid migration models. But that's separate literature. But the actual phase change effect is not taken into account in the thermal structure. But again, in similar response to Samer's question, I don't think it's that important with tenths of degrees max, which is relatively minor compared to the huge temperature variations we're predicting.
Right. We could always do that calculation again if people are interested to see, but yeah. Okay. There was one, any other students? We had.
I'm not quite clear about if the subducting plate is the only driving force for the flow. It is.
In our models, it's assumed it is, yes.
Yeah, in the model. Yeah. Okay. So how about the interaction between the flow and the plate? That is, the plate in your model, it has a assigned geometry and assigned velocity. Okay. But the flow itself is acting on the plate, right? So the plate could, in reality, deform.
Yes.
Right.
Yes, absolutely. And that is where we need evolutionary models and integration with dynamics. So we make a simple form of a subduction zone that informs us, but it's not a complete information. So you're similar to Claudia's question. If you want to look at exhumed rocks that come up in rifting regions, you need to include that explicitly. And that's where you need to go to more fully dynamic models. The fully dynamic models, unfortunately, don't necessarily adhere to the geometry we like to study when we look at seismics of a particular subduction zone. So there's some trade-offs there.
All right. Any other questions?
Peter, can you comment on what controls or defines the lithosphere-asthenosphere boundary beneath objects? The reason I ask is that geochemists think a lot about lithospheric mantle as a place to store chemical heterogeneities
There's been Gordon conferences where people throw the LAB at each other. And I'm sorry, I honestly do not know what controls the LAB. It's a very intriguing boundary because it's sharp. It looks like fluids and melts are involved right below that boundary. If there's one specialist to argue about the LAB, it's Samer here, who has written some nice papers about this. I'm not a specialist in this, I'm sorry. There's no real LAB here. It's just a consequence of the cold rheology being stiff viscous plate. And so these subtle effects that are clearly there to define the lithosphere-asthenosphere boundary are not taken into account in our models.
And there's the petrologic lithosphere and the seismic lithosphere and the mechanical lithosphere and all those things. So you have to be careful with your.
At least you don't call it the petrological moho, because as seismologists have taken that name. You can't borrow that.
All right. I think why don't we stop for coffee? Well, let's reconvene at 5 past, so we don't get too off schedule. Okay.